In this lecture, we want to take a look at binary search trees. A binary search tree is a linked data structure very similar to linked lists. However, there is a difference. With linked lists, you have a single forward-pointing node. However, with binary search trees, you have two links or two node references that go in the same direction. And what you do then is split either way depending on the ordering of the data. And so I want to talk about this idea for just a moment here, and I'm going to switch over to the sketch pad. So we have the idea of an array, and we might perform a binary search operation on an array. And the way we do this, as you know, is you go to the middle of the array and you check to see if the element you're looking for is either to the left or right if it's not found. What this allows you to do is to discard or throw away about half of the nodes, or not nodes, but rather elements in the list with each pass. So the next pass you perhaps go here, and again you can discard or stop looking at roughly half of the remaining nodes. This gives you big O of log n behavior. This is the cutting in half principle. And if this can be used in a way with linked structures to get better behavior, that would be highly desirable. Well, in fact, we can. So let's take this idea with the linked list. Here I have a root node, or the top of the tree as it were. This is the single entry point, or the starting point for the tree. And now I can say, okay, everything that is smaller than this node goes this side, everything larger goes this side. And then I have a link here with the same idea. The idea being then, if we rotate this around, we have essentially a binary search tree. So we have a tree here. This is the root node, and this is a node just like a linked list node, except there are two forward references in this link, left and right. And what we will find is that everything located to the left of this node is smaller than that node. For instance, if the data here is 50, then the data in every node to the left must be less than 50. Similarly, here everything to the right of the 50 must be larger. Therefore, the net effect of this is that you are discarding half of the remaining nodes. When you go left, you go right. So in essence, it's the same idea that we had with the binary search tree. You cut the number of nodes you have to look at in half with each decision you make. So you compare the element you're looking for with the element you're at now, and you either go left or go right. And it's the same idea. You go left, go right. Up here, when you get to this point and you look at the element, you decide, do I go left or do I go right? But when you make that decision, you have discarded or thrown away half of the elements that remain inside the array. With the tree, you're discarding half the elements that are in the tree. This presumes, of course, that the tree is balanced and even. That is, there are the same number of nodes on the left and on the right side. And it turns out this is not the case. There's no way you can guarantee that. However, on average, it's true. And therefore, what we get is big O of log n behavior. Recall that with linked lists, the behavior is the problem. If you're not inserting first or inserting last, but inserting somewhere in the middle and you have to find that insertion point, then that operation is big O of n. To scan down a list and find a particular node in that list is big O of n. To find and delete a node in that list is also big O of n. But these same operations with the binary search tree provide big O of log n behavior instead, which makes them highly competitive with other superfast structures. Thus, tree structures of various forms are alternatives to hash tables for dictionary structures. And the reason for this is that performance is very, very good. Log n behavior is very close to big O of 1. It's not big O of 1, but it's very close to big O of 1. Therefore, these are high performance structures that provide excellent performance. Thus, you can see here a binary search tree example. We have the 25 at the root node, and everything to the left must be smaller. 8, 17, 21. This definition we can apply recursively to the entire tree. That is, with the 17, everything to the left of 17 must be smaller than 17. Everything to the right must be larger, and it is. With the 8, everything to the left must be smaller. There isn't anything to the left. Everything to the right must be larger. Thus, the leftmost node is the smallest node in the tree, and the rightmost node is the largest node in the tree. So we can use this recursive definition as we look at these trees to see, and this holds for every case, that to the left the data is smaller. And that doesn't mean the immediate left, it means the entire subtree. We can think of the 17 as the root of its own binary search tree. It is part of the larger tree, but this subtree, rooted at 17, follows the same rules. To the left is a smaller node, to the right a larger node, and so we can think of each node as a subtree, and the same rules will apply. The structural and ordering properties are as follows. The binary search tree is like a linked list in that it has data and linked nodes. However, the binary search tree has two forward or downward links, a left and a right. Each node in the tree may have 0, 1, or 2 children. That is, it can have no children, it can have a left child, or it can have a right child, or it may have both. The left subtree of any given node must contain data that is less than its parent. And then the right subtree must contain data that is greater than the parent node. And again, as I mentioned, we can look at this recursively and say that any node is in and of itself a binary search tree, and thus every element to the left of any node must be smaller than the data at that node. And similarly, any data to the right of that node must be larger. Binary search trees are typically used to implement the dictionary ADT, and so we have a node then with 4 fields: the key, the value, left child, and right child. This is an example of a node class. We have the key and value here, the left and right child, and then the constructor where we initialize the key and the value and set both the left and the right children to null. There are different terms that are used with tree structures. They're also used commonly for graphs, which are a form of trees, and graphs may be covered at the end of CS 310, though more extensively in CS 560. So the terms you need to know: root is the top of the tree. It's similar to a head of a linked list. It's the single entry point into a tree. Subtree. Each node in the tree may be thought of as a tree itself. And this idea of subtree is an important one because the rules apply recursively to every node in the tree. Everything to the left is smaller, everything to the right is larger. The height of a tree is the number of links in the longest path from root to leaf. That is, starting at the root node, you count the number of links between the root node and a bottom or terminal node, and the number of links is the height of a tree. Some authors count the links and others count the number of nodes. It is more common to count the number of links. Let me illustrate for just a moment here. Let's create a tree. All right, here's an example tree. This is the root node. And then we count the edges or the lengths along the longest path. So the path here is 2, 1, 2. The path here is 1, 2, 3, 4. The path here is 1 and 2. And so what you do is you count the number of edges or links between the root and terminal nodes, that is, a node that has no children. So this is a terminal node, this is a terminal node, this is a terminal node. There are precisely 3 paths here to be considered. The longest one is the height of the tree. This one has 4 links or 4 edges. Therefore, the height of this tree is equal to 4, which is the number of edges. This tree has 5 levels, 1, 2, 3, 4, 5 separate levels, but the height is 4. Some authors use a different definition. However, this is the standard one, and this is the one that you should use for the course. Node is a wrapper that holds 2 references, one to the left, the other to the right, and it contains a key and value. Very similar to the node in a linked list, except there's an additional data item and one additional forward or downward link. Edge. This is the term for the link between a parent and child node. It's the same as the link, but it's called an edge. The path is the sequence of edges between 2 nodes. The parent is the ancestor, the child is the descendant. A leaf node is the node at the bottom of the tree that has no children. Visit. This is sometimes called walking the tree, and this is to do something with a node. This is done, for instance, with iterators, or if you print the tree, you will walk the tree and visit each node in the tree. The number of levels in a tree is the height plus 1. Note that there are these 2 definitions of height. So if the nodes are counted, then the height of the tree is equal to the number of levels. If the edges are counted, then it is height plus 1. It's more common to count edges than to count nodes. An inner node is not a leaf node. That is, a node that has either 1 or 2 children is an inner node. A leaf node has 0 children. A complete tree is a tree in which all levels in the tree are full. And similar to binary heaps, all of the leaf nodes are at the same level, and all nodes have 0 or 2 children, but none of them have 1. So all of the levels are completely full. A balanced tree is a tree that is not necessarily complete, but the height of the tree grows at a rate of log n. It need not be precisely log n. However, the height, as the tree increases in size, the height increases at a rate of log n. This is important for later structures that you will study. Binary search trees in and of themselves are not suitable for data structures use, not suitable for production code, in the same way that linked lists are not suitable for production code. It's because they're too slow. Searching a linked list is very slow. Searching a binary search tree can be slow. It has terrible worst case behavior, which we will discuss later. So let's look at some standard tree operations. The first is search. So the idea here is a fairly simple one. And again, I'm going to return to the sketchpad to take a look at this. So let's consider a search operation. Imagine that we are looking for, let's say, the 49. This is what we're looking for. We go here to the 50 and we examine it. And we say, is the 49 less than or greater than the 50? Well, obviously it's less than, so we go to the left. Now we're at the 40. We look at the 40 and we say, is the 49 less than or greater than? It's greater than, so we go to the right. We go to the 48. We compare that to the 49 and we go left or right depending on the difference between the two. The 49 is larger, therefore we must go to the right, and we have found the 49. Notice that as we did this search operation, as soon as we went here to the 40, that eliminated these nodes. And when we went to the 48, that eliminated these nodes. And so this is the idea of throwing away roughly half of the remaining nodes each time. That makes the search login time. So here we have the standard get value, which is the dictionary method. You're given the key and you find the value that matches it. And of course the data is stored in binary search trees based on the keys, as was the case with the hash tables. So first there's a test to see if it's empty, and if it is, you simply return null, not found. Then we set a pointer equal to root. Altering the root variable would of course change the tree, which is not what we want to do for a simple search. So now we have the test at the top of the loop, while the current key data, the current key is not equal to k key. So the key at current is not equal to the key we're looking for. We have to either go left or go right. So if the key we're looking for is smaller than the current key, we go left. Otherwise, we go right. Now then, if the act of going left or right has caused current to become null, it means that we have not found what we're looking for, and therefore we return null. But if we fall out of the loop because the key we're looking for and current key are the same, we fall out of the loop, then we simply return the current value, and it has been found. So this is a fairly simple idea. The difference here with the linked lists is we do not have while current's not equal to null. We know that current's not equal to null because we tested for it here. Therefore, as we enter the while loop, we know it's not possible that current is null. It must point to a valid node. So we compare that key to the one we're looking for, and then we either go left or right as needed. However, at the bottom of the loop here, if current has become null because of one of these assignments, then there's no place further to look. We have run out of options, and so the element we're looking for is not in the tree, and we return null. So I want to go back to the sketchpad and look at an unsuccessful search. Okay, given a simple binary search tree here, let's look for an element that's not in the tree. So let's look for a 12. We're going to look for the element 12. So we go to the 50, and the 12 is not equal to the 50, and the 12 is smaller than the 50, so we must go left. We're now at the 40. We compare the 12 to the 40. And the 12 is smaller than the 40. So, I'm sorry, this is a 45. So we go to the left. So we're at 25. So we compare that to the 12. And the 12 is smaller than the 25, so we go left. And we're at 10. And at 10, we see that 10 is smaller than the 12. The 12 is larger than the 10, so we go right. But on the right child is a null, and that tells us that it is not found. Therefore, at the point where we said current gets current dot right, current became null. And then we return null because the 12 is not in this tree. Recursive searching operations. It turns out that for binary search trees, recursion is extremely valuable. In fact, essential. There are some things that are just all but impossible to do without using recursion. And so here is a recursive version of the getValue method. Students often are afraid of recursion and don't want to try to use it. However, it's simpler code in many cases. And so this is a simple method here, and I think you can follow the logic of what's happening. This is nothing more really than a wrapper because we have to pass in particular nodes into the tree, but we cannot have that in the public signature. Nodes are not exposed to the outside world. Therefore, here we have getValue given a key. And then we call a helper private method, and it must be private, the key we're looking for in the root node of the tree. Now there are two really essential components for recursive algorithms that you must observe. The first is there must be a well-defined stopping condition that can always be reached. The stopping condition here is the not found condition. The other stopping condition, of course, is the found condition. That's one way to stop, but if the element is not in the tree, then this gets triggered. Thus, it can be reached in every case. It's either found or not found, and there is no third possibility. Then each pass or each subsequent call to a recursive algorithm must represent a smaller set of the problem, a smaller piece of it. And that's the case here because you're passing in either the left or the right child pointer, and so you have roughly cut the tree in half. So let's look at the code here. We call this private method, passing in the key that we're looking for in the root. Then we have find, so the key we're looking for, and some node in. The first call, the original call, in is the root node. So we check to see if it's null. And if it is, we return null. Again, this is the not found or stopping condition. Now we compare the two keys, the one that's passed in here, the in, and the key we're looking for, which is here, what is passed in. So we compare the data at in.key and key. And if the key we're looking for is smaller than the key at the current node, then we call this with the left child. Otherwise, we call it with the right child. And then down here, if we didn't return, it's not null. And if it's not less than and not greater than, then it has to be equal. So we have a three-way split here. It's either less than, greater than, or equal. And if it's equal, we just return the value and we're done. If it's not found because we have descended the tree with either the left or right child until we hit null, then we return null and we're out of there. You should trace through this and see if you can follow the logic and see what's going on. Learning how to use recursion is important, and you simply cannot avoid it for binary search trees. So here's an example of why we need recursion. This is a problem that recursion solves very cleanly and very neatly. So the question is, how do you print this tree? You need, of course, to print it in order. Binary search trees keep the data in order, and you need to print the contents of this tree in order, which means you have to print 8, then 17, then 19, then 21, then 25, and then 32. How in the world do you do this without using recursion? Well, these don't appear to be in the right order to support an iterative method. There is one, but you would have to create an auxiliary stack and keep track of where you're going. Think recursively for a moment. The idea is a simple one. If you are given 3 nodes, a set of nodes where you have a left and right child, so take for instance the 25, we have 17 on the left and the 32 on the right. Then we can print this tree by saying, okay, first go left, do your thing, then print, then go right. So if we go left, then we go left, then we go left, there's nothing left, nothing right, we print. We have finished the go left, we come up here and print the 17, and then we go right. In other words, go left, print, go right. That's the simple logic or the simple heuristic. So here's a print method. Note that I've made this private because you must never put a print method in a data structure. It's a mistake because no one method for printing is going to be appropriate. If you need to print the contents of a data structure, you would use the iterator to do that. So this is a sin. However, it illustrates in a simple way what I want to show you about recursion. So here we have a well-defined stopping condition. If we've run off the end, we just return and don't do anything else. And down here, this recursive definition, go left, print the data, go right. So it's a simple idea if you think of only 3 nodes. Go left, go print, and then go right. And then we apply this recursively to the entire tree structure. So here's an example, and you should spend some time looking at this to see that you can follow it. What I have done is on the right side here is a fairly simple tree, the one we've been looking at, and on the left are the recursive steps to print it. Note that in every case, every single call has 3 elements. Go left, print, go right. Let's look at the 25. We have go left, print, go right. So every single node, every call has these 3 pieces. Well, of course, what happens when we go left here? When we go left, it's not null. So in essence, here, when we have do print in dot left, we enter it first with the 25. So we enter this with the 25, and we go do print in dot left, and that's a 17. So we go back in with the 17, and the first thing we hit is go left with the 17, which is the 8. So in other words, we do the go left, go left, go left steps. That's what happens first. Then, because the go left off the 8 is null, the middle step, the print, happens on the 8 next. So, the first thing we do is go left to the 17. And the first line, of course, in our method is go left because it's not null, and we get to the 8. Now we call go left with 8. This is the parameter here. The left child, and it's null, so it immediately returns. So we did the go left call, then we print, and then we go right, and the right call is null, so it comes back, and this call is finished. We've printed the 8. Well, once that's finished, we're back in the 17. Well, we did the go left, now we do the print, and then we go right. So we go right, we call it with the 21, and of course the first thing with the 21 is go left. And then we go left with the 19, we go left with null, we come back and print 19, we go right with 19, we come back, we have done the left print right, we're back in the 21, we did the left call, so now we do the print statement. Then we go right, it's null, we simply come back, Now we come back to the 17, but we have done the go left, print, go right. So that call, the 17 call, is completed. And that's at this point. The 17 go right is completed. Then we're back at the 25. We print. We did go left. Then we print, and now we go right. So we go right to the 32, and we immediately go left. It's null. We print 32. We go right. It's null. We have returned. We finished the 32. We're back at the 25, and we finished that as well because we already did the left call. We did the print. We went right. Therefore, we've reached the end of the method, and it merely stops. So this prints 8, 17, 19, 21, 25, and 32 in perfect sorted order. Insertion operations. You must check for duplicates. Duplicates are not allowed in dictionary data structures. Allowing duplicates makes the code more difficult and is not typical, so we won't discuss that. You find the insertion point by traversing the tree, going left or right as needed. Insertion always happens at the end of an existing path when you encounter a null link. Similar to insertion in a linked list, you must keep a preceding or a trailing node pointer or node reference so that you know what the parent is. That's what you must update. But you also have to keep track of whether you went left or went right. And this is typically done with the Boolean value. So you need the trailing pointer, which is the parent reference, and the Boolean that says whether you went left or you went right. It's different from insertion in a linked list in that you never insert anywhere other than the end of the path, not at the beginning and never in the middle. You can use either an iterative approach or a recursive one. Both are valid, though the recursive approach is in fact shorter. So here's the recursive approach, but first I want to look at an insertion with the sketchpad. So we will use this exact same tree that we had for our previous example. I want to look at an insertion operation, and we'll use the same tree we had from before. I want to insert a 63 into the tree. So I want to look at the steps that are required. All right, we have these variables. We have current. We have the parent pointer. And then we have the Boolean. Did we go left or didn't we? So we are going to initialize current to head, which is 50. The parent, of course, is null. And left is set to false, just as an initial value. So we compare the 63 with the 50, and we see that the 63 is larger. Therefore, we have to go to the right. So we go to the 85. So current becomes 85. And the parent of 85 is now 50. And did we go left? No, we did not go left, so it's false. So we are now pointing to the 85, and we compare the 63 to the 85. The 63 is smaller, so we must go to the left. So we are now at 60. So current now points to 60. The parent of 60 is the 85. And did we go left? Yes, we did. We went left. All right, we're now at 60. And we compare this to the 63. The 63 is larger, and so we go to the right. So current becomes null. This is going to be our insertion point. We go to the right. The parent is a 60, and it's left. No, it's right. Therefore, we insert on the right child the 63. So it goes to the right of the 60. It could not go to the left of the 60. It would not work. That would not be possible. Our stopping condition is when we've hit null. So this is what you need to bear in mind. You need these two additional pointers. Current runs until you hit null. Parent is the node that precedes. That is the last visited node. And then you need to keep track, did I go left or did I go right? And the reason you need this, it's not left, it must be right. Then 60.right gets the new node 63. So here we have a recursive version of this insertion. We have public Boolean add and then a key and value. Again, this is more or less a wrapper. The work is getting done in this private method that we have called insert. First, there's a check to see if it's a duplicate. If the key K is in the tree, then we abort and return false. If the root is null, then we know that the tree is empty, so root gets a new node. Otherwise, it doesn't contain it, the root is not null, then we call insert. We pass in the key and value, we pass in the root, the parent, and did we go left or not. On return from this insert, we increment the current size and return true. So let's look at the insert method. This is the private helper method. We've passed in the key and the value. This node, of course, is the current one. This is the parent node, and then the Boolean, did we go left or not? So we check to see whether the current node is null. If it is, we found our insertion point. If we went left, then parent.left gets the new node. Otherwise, parent.right gets the new node. Else if. Now we're comparing, and we have to either go left, or we go right. So we pass in the left child, the right child, and so we descend the tree and do the insertion this way. So the choices here are, 1, if in is null, we found the insertion point. So then we insert either on the left or right, depending on whether we went left. So this is fairly simple code. Trace through this with pencil and paper. See if you can follow it and see what's happening. Deletion is the most difficult operation. The reason for this is the number of cases to consider. The node that you're going to delete may have 0, 1, or 2 children. A different strategy must be used for each case. And then the node to be deleted might be the root node, in which case the root must be reset. So looking first at the operation with 0 children, then this is the simplest case. You use the same heuristics that we've been talking about for traversing or walking the tree. You look for, and I've identified the node, but on the way down the tree you keep trailing pointer to the parent and also keep track, did you go left or did you go right? And so in this case we start with, suppose that we are going to delete the 19. We have to find it first. We start with the 25 and the 19 is smaller, so we go left. And 19 is larger than a 17, so we go right. And 19 is smaller than a 21, so we go left. We found it. Now we can test to see that the left and right children are null. So if left child equals null and right child equals null, then we have a node with no children. Then all we have to do is check, and if we went left, then parent.left gets null. Otherwise, parent.right gets null. So essentially we sever this link and we're done. The operation with one child is only slightly more complicated. So in this case, we are going to delete the 21. So we go to the 25 and we see 21 is smaller, so we go to the left. And we see the 21 is larger, so we go to the right. And we have found it. We have found it. Now what we want to do is replace this node with its child. That is, we know that it has one child. We can test for that. If either the left or the right is null, then it's one child. We already took care of the case of no children, so if either the left or the right child is null, we know that we have the case of one child. Notice that it does not matter whether the single child is a left or a right child. It doesn't matter. It merely replaces the node to delete, which is the 21. And so as you can see, the 19 just goes here. Now, what values might we have for a right child? Well, as you can recall from the structural and ordering properties, anything to the right of the 21 must be larger than the 21, but because it's on the left side of the 25, this limits the range of values that could be here. If there were a right child, it could only be 22, 23, or 24. But notice that at 22, 23, or 24 could go right here without breaking anything. That is, the structural and ordering properties are intact. Therefore, in the case that you have a node with one child, the 19, you simply replace this node with that one child, whether it's a left or a right, and it doesn't matter which one. The deletion operation in the case of two children is more complicated. It is difficult because of the structure of the tree. So in the example here, imagine that we're deleting the 17. Well, if we delete the 17, we can't just replace it with a child. If we replaced it with the 21, what happens to the 19? We could, in fact, replace it with the 8, and that would work, but there is no way to know for certain that this would work correctly. Therefore, we don't want to replace this node with one of its children, because the 19 is an issue. So the strategy here is turn this into the case of deletion of a node with one child. Well, how do we do that? As follows. You do an in-order traversal. That is, you find the in-order successor. By in-order successor, I mean if you print this tree out, the element that follows the one you're deleting is the in-order successor. So for instance, if we print this tree, we have 8, 17, and then the very next value is the 19. So the strategy here is take this 19 and put it here. Look what this does with the structure of the tree. If I put a 19 here, is everything still in order? Yes, in fact it is. So what we want to do is turn this into a case of deletion of a node with one child. Now in this particular case it has no children. However, that doesn't matter, because if it did have a child, that wouldn't pose a problem. The point is it can only have one child. So the in-order successor cannot have two children. Okay, why is this so? Why is this true? Suppose that there were an 18 in this tree, then where would it be? It would be to the left of the 19, and it would be the in-order successor instead of the 19. Therefore, for the in-order successor, it cannot have a left child. If it had a left child, then that child would be the in-order successor. So the only thing that would fit here on the left is an 18. An 18 then, if it were here, would be the successor. But it isn't. Therefore, this node, your in-order successor, can have a right child, but it can't possibly have a left child. You can ignore the possibility of the right child because it will come along for free. That is, when we adjust the tree, no steps need be taken here. Okay. So, step 1, take the data in the in-order successor and overwrite the data in the node to delete. That is, we are not changing the left or the right link. We just clobber the data. Overwrite the key and value with the in-order successor. So this node is now garbage, and we delete it. Therefore, we have a node with no children. We delete it, and the tree is intact. So we simply copy the in-order successor up here. I want to look at an example of this with the sketch pad and see if we can look at how this might work. Suppose that I want to delete the 50. What's the in-order successor? How do you find it? You go to the right and then go left as far as you can. So the in-order successor here is a 60. Note that you can do either the in-order predecessor or the in-order successor. Therefore, we can replace this 50 with either the 48 or the 60. Both are valid. The 48 is the in-order predecessor. And the 60 is the in-order successor. Either way works. In general, it's probably best to stick with one, and the amortized cost with many insertion deletions would not be excessive. However, to get the most balanced tree possible, to minimize the unbalancing that might happen, you can alternate between in-order predecessor and in-order successor. However, this makes the code more complicated. So I typically will use the successor, which is this one, the 60. The idea then is this. Step 1, go up here and overwrite the data with your successor, which is the 60. Now then, we have a duplicate node which has to be removed, but this is a node with one child. It cannot possibly have two. And so we replace this node with its child. This is deletion of a node with one child, which we can call that method if we want to. And now we have our tree with the root changed to 60, and the structural and ordering properties are in fact intact. So in this case here, we are replacing this node with its in-order successor. We go to the right and go left as far as we can. Now it's possible that this may be the successor node. It can happen, but the general heuristic, the design is for in-order successor, go to the right, then go left as far as you can, and that will be the in-order successor. So to simplify deletion of a node with two children, what you must do is find the next node that would be printed. That's the in-order successor. You go to the right and then left as far as you can. The in-order predecessor, you would go to the left and go down that side as far as you can. Go to the left and right as far as you can. It's easier if you do just the in-order successor. Go to the right, then left as far as you can go, and you're guaranteed the node you find here cannot have two children. It may have 0 or it may have 1. It doesn't matter because you're going to delete it. So the 21 left will be severed, set to null, and it will be deleted once you've copied the data here. A word about iterators. With recursion, when you walk the tree, that is, we looked at the print method earlier, when you traverse the tree, you can't stop in the middle and then jump back in because of the system stack. And so, as a consequence, when you have a recursive algorithm, it needs to run to its conclusion. So the way to do this then is to make an auxiliary array and use recursion to fill it in. You fill in the array in the constructor for your iterator. So I have here a simple in-order fill method. This you would call in the constructor. So you would create an auxiliary array of current size, and then you would fill it in with these nodes. So you go left, assign to the array, and go right. Now, of course, there are two variables here that are not defined here. That is the iterator index. Whoops, my apologies. the iterator index and the array. So you're going to create both of these in the class and initialize them in the constructor. A word about performance. Binary search trees offer log-in complexity for insert, search, and delete operations in the average and the best cases. However, in the worst case, all of these operations become linear. They become big O of n. And this worst case is when data is inserted in sorted or almost sorted order. So I want to look at this behavior. Imagine that we're going to insert into a binary tree the even integer starting with 2. So here we have 2, and that's the root node. Now we insert 4. Well, it's got to go to the right, so we have 4. And then 6, and then 8, and then 10, and then 12, and then 14. Okay, so we keep going at this point. So if you're going to search this tree, there is no possibility of going left. You can only go right. Well, what's the height of this tree? What's the height? We must count the number of edges or links. 1, 2, 3, 4, 5, 6. The height here is 6. There's 7 nodes in this list. And so what happens if you insert things in order or almost in order, you end up with essentially a linked list. A linked list that's a bit slower because there's additional overhead. There are more assignment statements as you traverse down looking for an element. Even worse, because you will end up using recursive algorithms for this, and each one of these will push on the stack. It will not finish. That is, you start but don't finish calls for this node, this node, this node, this node. Thus, if you have n nodes in the tree, you're going to make n recursive calls without any of them completing. The consequence of this is you will crash with a Stack Overflow exception. So this, of course, is expected. If you insert 1,000,000 nodes in order in your tree, you will definitely crash out to the command line. You should not consider this a deficiency in your code. Rather, this is expected behavior. The reality is that binary search trees as such are not suitable for general use. If you can be certain that the data you're inserting is not in order, then they certainly may be used and are a good candidate. There is nothing wrong with binary search trees. It's that worst case behavior that we must avoid. And so later on in the next couple of lectures, we will be looking at ways to deal with this worst case behavior. And this involves adjusting or restructuring the tree to lessen the height of the tree after insertion. There's a lot of overhead with doing that, and it can be quite complex. If you have a set of data you need to insert that you can do something with beforehand, then that can work better. That is, imagine the case where you have an array of 1,000,000 elements that you have accumulated. You then need to insert this data into a binary search tree to do fast searches and also to do minor insert and delete operations. If you scramble the array before you insert it, then you're guaranteed not to have this worst case behavior. By scramble, I mean you start at index 0 and go down the entire array and swap the element at that index with some arbitrary other index. That is, you use random number generator to pick at random another index to swap with. So you start at index 0 and maybe you swap with the element at index 100,000, 14, and 7. And then you move down to number 1 and you swap with the element at 900,000, 994, and so on. Essentially, at each spot of the array, you swap it with a random other array element. And in so doing, you completely scramble up what would otherwise have been a sorted or ordered array. And then when you insert it into the binary search tree, you will have a more or less balanced tree. That is a tree whose height is C log n. The other heuristic for dealing with the unbalancing is built into the trees themselves, and there are a number of different ways this has been approached. These are such important structures that there are a large number of ways this is handled. We will be looking at a couple of them. AVL trees and red-black trees, which maintain balance, that is, maintain a height in big O of log n. But that's a subject for another lecture. So this concludes our discussion of binary search trees.